Um this session, the focus would be on something very fundamental in number theory, and we would try and assimilate various ideas related to what's referred to as a Euclid's lemma. This actually is the starting point for towards the tenure of a large number of number theorists. As beginners of number theorists, you might want to get a hang of Euclid's algorithm, Euclid's lemma. And let me tell you, it's something very simple. You've been using that time and again, but now a formal intrusion into Euclid's lemma, that's the objective. So essentially, you realize, suppose I have a number 26, right? And I divide it by 4. What happens? When I divide it by 4, two things happen. One, there is a quotient, which is 6 here, right? Plus, there is a remainder, which is 2. Yes or no? So when you divide 26 by 4, it leads to an integer quotient, which is 6, and another integer 2, which is the remainder of this division. Yes or no? Which means 26 could have been written as a quotient 6, quotient 6 into divisor 4, right? Quotient into divisor plus 2, which is the remainder. Yes or no? Does it make sense? All right. In a very general sense, suppose A and B are two natural numbers. Suppose A and B are two natural numbers. And I divide A by B. What happens? It leads to a quotient Q. Plus remainder R divided by the divisor B. How about it, right? This is what happens in the event of a division. If an integer A is divided by another integer B, then we have Q, an integer, which is the quotient of this division, and R, which is the remainder of this division. Yes or no? Sounds good? Right? And realize that the remainder of the division never exceeds B. The remainder could be 0. If the remainder is 0, that means B divides A. If the remainder is 0, it means B divides A, right? But if remainder is not 0, what are the other permissible values of the remainder? The remainder can be 1, the remainder can be 2, the remainder can be 3, the remainder can be any number less than B, any natural number less than B. So it could also be B minus 1. But remainder can't be B. Remainder can be at best B minus 1. So what are the permissible values of the remainder? The remainder has the following permissible values. The remainder, if it is 0, then A is perfectly divisible by B. The remainder can be 1. The remainder of this division can be 2. The remainder of this division can be 3. And the remainder can go all the way to B minus 1. These are permissible values of the remainder. Remainder belongs to this set. If R is 0 as a special case, then A is perfectly divisible by B. We say B divides A. The fact that B divides A is commonly written as follows. B, this symbol and A, it means B divides A. That means A is perfectly divisible by B. It means that when you divide A by B, the remainder is 0, which is this case. If B does not divide A, then the remainder can assume values like 1, 2, 3, up to B minus 1, right? The remainder never exceeds B minus 1 in its value. So then this is something that you have dealt with time and again, and you're pretty familiar with this fact. Now, so we then say remainder can assume values from 0 to B minus 1, where B is the divisor. So remainder can assume values from 0 up to B minus 1, right? These are acceptable values of the remainder. Q is an integer, which is the quotient of this division. Now, I could further write this as A equal to B into Q plus R. A equal to B into Q plus R, which means that given two natural numbers A and B, A and B, there exist unique numbers Q and R. Given two natural numbers A and B, there exist two unique numbers Q and R such that A is B times Q plus R, where what is Q? Q is the quotient obtained on dividing A by B. What is R? R is the remainder of the division. That means the division in which A is divided by B. B is the divisor, right? So, if there are two natural numbers A and B, then they could always be connected by a relationship of the kind A equal to B into Q plus R, where Q is the quotient obtained on dividing A by B, R is the remainder obtained on dividing A by B. And the remainder R can assume values anywhere from 0 to B minus 1. This fact, this statement essentially is what's referred to as the Euclid's lemma. This is referred to as the Euclid's lemma. Like I told you, and I reiterate, this is something very fundamental to basic arithmetic, basic number theory, and the journey of any number theorist begins with the Euclid's lemma. That means A and B, two natural numbers, could always be connected by A equal to BQ plus R, where Q and R would be unique numbers. R would be a value lying between 0 to B minus 1. Yes or no? That's Euclid's lemma. Now, so far so good, right? So far so good. Now, suppose I have a number A. Suppose I have a number A. Now when I divide it by 2, what happens? If I divide it by 2, there is a quotient Q. An integer Q, plus there is a remainder R divided by the divisor. And therefore, the number A could be written in terms of 2 as 2Q plus R, where Q is an integer, but the remainder, this is the remainder R on dividing A by 2. What are the permissible values of R? In this case, R can take values from 0 all the way to 1. It cannot be more than 1, right? So the permissible values of R, the integer R, would be 0 and 1, right? So then, any number A could have been written as 2Q plus r, which is 0, or it could be written as a equal to 2q plus 1. A equal to 2q plus 1. That means if a number is of the form 2q, then it's an even number. If a number is of the form 2q plus 1, it's an odd number, as you can see. Yes or no? Right? In this case, realize that the remainder is 0 on dividing by 2. Remainder is 0 on dividing by 2. If the remainder is 0 on dividing by 2, that means 2 divides a. If 2 divides a must be an even number. Now, 2q plus 1, this is an odd number. This is an odd number because this is an even number plus 1. This is an even number. 2q is an even number plus 1, and therefore it's an odd number. So in general, the numbers could be represented as 2q and 2q plus 1. All sets of numbers, all sets of integers could be written as 2q and 2q plus 1, where 2q is the set of even numbers, 2q plus 1 will be the set of odd numbers. If I assign different integral values to q, I get different even numbers and different odd numbers. So in a very general sense, in a very broad sense, numbers in the number system, the natural numbers or the integers, in fact, in a very general sense, in the number system, could be written as either 2q, which is a general framework for representing even numbers, or 2q plus 1, which is the general framework for representing odd numbers. Yes or no? Different even numbers will have different values of q assigned to them. Different odd numbers will have different values of q assigned to them. But if a number is of the form 2q, where q is an integer, it will always be even. If a number is of the form 2q plus 1, where q is an integer, it's also always going to be an odd number. Now, so that's as far as expressing that entire set of numbers in the form 2q and 2q plus 1, that is in terms of 2, right? Suppose now I divide a number a by 3. What happens? Suppose I divide a natural number a by 3. It leads to a quotient q plus a remainder r by the divisor 3. Now, the remainder can at best have a value 2. What are the permissible values of the remainder here? The remainder can have values like 0, 1, 2. What happens if the remainder is 0? If the remainder is 0, it means a is perfectly divisible by 3. That means 3 divides a. If r is 0, 3 must divide a. That's the symbolism. This means 3 divides a. This is what it means. If r is not 0, then a is not perfectly divisible by 3. So in one way or the other, any number a could be written in terms of 3. Any integer a could be written in terms of 3 as 3q plus r, where r can assume values like 0, 1, 2. So then, when r is 0, then this takes the form 3q. When r is 1, it takes the form 3q plus 1. When r is 2, it takes the form 3q plus 2. That means all numbers a in the number system, all integers a in the number system could be written in terms of 3 as 3q, 3q plus 1 and 3q plus 2. Numbers of the form 3q are perfectly divisible by 3. Numbers of the form 3q plus 1, when you divide these numbers by 3, they leave a remainder 1. All numbers of the form 3q plus 2, when you divide by 3, they leave a remainder 2. Yes or no? So in terms of 3, that's how you write various numbers in the number system, various integers in the number system. Similarly, say, if I divide a number a by 6, what all do I get? I get a quotient q plus a remainder r divided by the divisor 6, where q is an integer, r is an integer, the value of r does not exceed 5, right? The remainder on dividing by 6 can be what all? Can be 0, 1, 2, 3, 4, 5. These are permissible values of the remainder when you divide a number a by 6, right? So which means r in this case can assume values like 0. When r is 0, what happens? When r is 0, that means a is perfectly divisible by 6, right? R could be 1, R could be 2, R could be 3, R could be 4, R could be 5. Yes or no? Right? So which means A could be written as any number A, any integer A in the number system could be written as, in terms of 6q, as 6q plus R. Where what are the permissible values of R? R is 0. If R is 0, A is perfectly divisible by 6. Otherwise, R is 1, 2, 3, 4 and 5. That means any number eventually, when you divide by 6, would only give you R equal to 0, 1, 2, 3, 4, 5. That means any number in terms of 6 could have been written as 6 times an integer plus another number which is less than 6. Another integer which is less than 6. That means numbers in terms of 6 could have been written as 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4 and 6q plus 5. Yes or no? Right? So numbers in the number system in terms of 6 could have been written as 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, 6q plus 5. In exactly the same way, any number A could be written in terms of B. Any number A could be written in terms of B as BQ plus R, where R would assume values from 0 to B minus 1. R would assume values from 0 to B minus 1. That means when R is 0, then the number becomes BQ. When R is 1, the number becomes BQ plus 1. When R is 2, the number becomes BQ plus 2. When R is B minus 1, then the number becomes BQ plus R minus 1, where Q is an integer referred to as the quotient obtained on dividing A by B. Make sense to you? Right? So, similarly, if someone said, write all numbers in terms of 5, find a generalized representation of numbers in terms of 5. The numbers in terms of 5 could be written as, say, 5q. All numbers when divided by 5, leaving 0 remainder, is 5q. Numbers that leave remainder 1 on dividing by 5 would be of the form 5q plus 1. Numbers that will leave remainder 2 on dividing by 5 would be 5q plus 2. Numbers that will leave remainder 3 would be 5q plus 3. Remainder 4 would be 5q plus 4. Remainder 5, no remainder 5. When you divide by 5, remainders would be 0, 1, 2, 3, 4, and so on and so forth. So this is how you could write numbers in terms of 5. If you want to write numbers in terms of 7, then all numbers in terms of 7, the entire number system, entire set of integers in terms of 7 could have been written as 7 times an integer. This would be all numbers that are perfectly divisible by 7. 7q plus 1, these are all numbers that will leave a remainder 1 on dividing by 7. 7q plus 2, these are all numbers that will leave a remainder 2 on dividing by 7. 7q plus 3, these are all numbers that will leave a remainder 3 on dividing by 7. All numbers 7q plus 4, remainder 4, 7q plus 5, remainder 5, 7q plus 6, remainder 6. And on dividing by 7, the remainder cannot exceed 6. So this is the representation of the entire set of numbers in terms of 7, right? Now, in a very general sense, say if b is bigger than, if b is smaller than a, say this is a, then what I could do is, when I am dividing by a, there are a certain number of b's included. There are a certain number of b's included. Say this is the real number line, which is 0. This marks b. This marks 2b. This point is 3b. To the immediate left of a is some qb. To the immediate right of a is, say, q plus 1b, and so on and so forth. Essentially what it means is that when you divide a by b, see, there is a b here, another b here, another b here, another b here. Essentially, this number a has a full qb included, plus this additional number r, which is referred to as the remainder. This additional number r, see, this number r is referred to as the remainder. That is what it means. Geometrically speaking, Euclid's lemma is represented as such. A is qb plus r. Make sense to you? Right? See, a is a number represented on the real number line by this, and before a, there are a certain number of b's included. 1b, 2b, 3b. There are q times b included in this a, and then there is a residual portion. This portion is less than b. This portion can be, this length can be 1 unit, this can be 2 units, this can be 3 units, it can be up to b minus 1 units, because the number just after a, this after qb, the next integer, let's say another b units, is going to be q plus 1b. So this length is b, this length therefore will be less than b. This length can be 0, this length can be 1, this length can be 2, this length can be up to b minus 1, but not b. This length has to be less than this length, which is b units. That's the geometrical way of representing Euclid's lemma. So there is a unique way to write any number a in terms of b. Any integer a in terms of b could have been written as a equal to q times b plus a remainder r, where q is the quotient obtained on dividing a by b, r is the corresponding remainder. R can assume values from 0 all the way to b minus 1. That's the way it happens, right? In the next session, I am very shortly going to give you an application of Euclid's lemma. Thank you.